Hey, Kubecon. I'm Vanessa Sochat. I'm a computer scientist at Lawrence Livermore National Lab, and today I'm going to be talking to you about application building in Kubernetes using JobSet. So about a year ago, I started my adventure as a developer for Kubernetes. And specifically, I had one goal to implement a job manager, our job manager at the lab called Flux Framework inside of Kubernetes. And so I wanted to take Flux and I wanted to take Kubernetes and I wanted to smash them together because that's how software engineering works, right? Not exactly. So there's these two communities. We have cloud and HPC, and in between them is this beautiful opportunity for the convergence of technologies and culture. We call this converged computing. And there was some rhyme to our reason in choosing Kubernetes and Flux. Both of our communities use them for running workloads and jobs, and they're also both modular. So for example, I can take a component from Flux and I can implement it inside of Kubernetes and vice versa. So TLDR, long story short, we created the Flux operator to implement the entirety of Flux framework inside of Kubernetes. And it was an awesome experience. It was the first taste of convergence. So our next logical question was, okay, we have our workload manager. Now, how do we run applications? Let's go and talk to some fish in that bay. How are these cloud and HPC apps actually different? First, looking at application coupling. In cloud, we have very loosely coupled apps. In HPC, we have very tightly coupled apps, and we'll talk more about what that means later in the talk. For resource scheduling in cloud, we may want to run a pod with a certain amount of CPU. In HPC, we're actually scheduling more than software. We're scheduling hardware down to the PCI bus. For job queuing in cloud, we may do something like calculate a priority score. In HPC, we have very sophisticated queuing algorithms that often are graph-based. Finally, workflow management. Well, cloud does this really well with automated declarative management. Bring in the YAML camel. In HPC, we also have workflow tools, but sometimes it's not really great. It's like bash scripts all the way down. So our first step after obviously getting our workload manager in Kubernetes was like, let's run some applications. Let's get into our bathing suits, dive into that bay. Whee! And our applications, they didn't run. Oh, why doesn't it work? The question for developers of all time. Please, someone tell me, why doesn't it work? So we needed to actually look deeper into this mystery. We needed to dive into the trench of treachery. Wait, how did that get there? I mean, the trench of discovery to really debug this problem. And so my team and I, we loaded up in our submarine, except I was the one on the outside that, like in the movie, gets eaten by the shark or like the underwater sea monster. No, I'm just kidding. So we went down, down, down. And our first stop was to try to better understand how we could model our complex HPC applications in Kubernetes. And we already had some experience with this because of the Flux operator. We had used an index job. So we had taken Flux, put it in a container. The containers go in pods. And by way of the index job, that gives us duplicates. We can add some system configuration files, and then a headless service gives us unique host names so they can all talk to one another. And this encompassed the Flux mini cluster. It was awesome, but there were hashtag developer problems. There's always developer problems, aren't they? So the first one was that we have to have different entry point logic based on the index in one script. We also needed to manually create the headless service. And finally, we really needed a way to say, like, when this main index 0 is done, the entire job is done. So, okay, we understood the limitations of job. We kept going in our adventure, and we encountered JobSet. Hey, JobSet, what's going on? What are you doing under the ocean? You know what? Don't answer that. It's totally cool. I do not judge. Yes, we would absolutely love your help. So with JobSet, we could add this other abstraction of a job set. And by way of having more than one replicated job, we could separate the logic of our different components, specifically into a lead broker and follower brokers. We could still have them on the same network. And with a success policy, we could actually say, okay, when this lead broker is done, the entire job is done. Awesome. So we knew that JobSet would be this abstraction to allow us to build these complex HPC applications. But we still had this problem, which is why we're underwater in the first place, that our applications didn't run. So let's not forget about that. So we needed to take a trip into the cave of debugging. So we go in this cave, and it really wasn't such a bad cave because we found some friends in there, and our friends had some good ideas about what might be going wrong. I had some ideas too, and what I ultimately found is that when I added a local DNS cache, the cluster that for first didn't come up at all of a sudden came up. And so who was lurking in the darkness? It was the DNS fish. Yes, you, get out of here, you. Nobody wants to hear about you anymore, yet you somehow are always around. So I said, okay, great. Let's run our application again. Maybe we'll see it run this time. So just to give you a sense of what I'm seeing, what you're looking at here are application times for a fairly good problem size for our application. And you're looking at time as a function of the cluster size. And so what we're doing is something called strong scaling, where you hold the problem size constant and you give it more resources. And what you'd expect to see is that it gets faster. And to some extent, we do see that. So we do see that up to size 32, but then at size 64, like, oh, something happens, and that something suggests that the cost of communication offsets any potential benefit to adding more resources. And also, I just want to point out that these times are not very good. So, it's still slow. Thankfully, Antonio swam out of the collaborator sub, and he was like, I can help V. You see, there's all these things that you aren't considering, from the base image to how you're building MPI, networking flags, and importantly, the instance type. So we did many more experiments, and by the way, this is over many months, and we ran into new errors, like, yes, so both of us were like, oh no, oh no. But I had this insight, and many developers have this insight: when you don't understand something, you need to measure things. We needed to measure the network and understand what was going on with our application. And because I had just done this work with JobSet, this was at the forefront of my mind. I was like, hey, JobSet, can you come down here? And JobSet was like, I don't know, it's kind of creepy down there. But JobSet gives us this flexibility to model not just our applications, but also tools for performance analysis. And the insight that I had specifically was that so many of our applications, along with actually machine learning applications, have this launcher and workers design. So I could actually implement everything from proxy apps to networking and storage or IO tools using this common design. So this turned into what the metrics operator, yes, he's absolutely adorable. With the metrics operator, you create something called a metric set. And the metric set is going to allow us to look at that networking, which we thought was the culprit, specifically using something called the OSU benchmarks. So we needed to dive deeper. So first, change of wardrobe, and we again went down, 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 down. So going down into the abyss of expectations, which is a very dangerous place to be, might I add. And so my first expectation was that HPC applications need low latency. We always have these beautiful InfiniBand fabrics. Why would they not need it? So let's go back to this idea of tight coupling. What does that mean? I want to talk more about MPI, the message passing interface. So MPI, if we look again at this launcher worker design, HPC is going to be using a tightly coupled design. So we may start with thinking of the concept of nodes. So here we have nodes, there's a launch node and worker nodes. But in HPC, because we need to run complex scientific simulations, we actually care about the relevant unit of a process. So instead of looking at nodes here, what you're looking at are 14 CPU that do the work, and they are going to be communicating using the message passing interface, which is called an interface because it's more like a standard, and there's different implementations of it. So I need to stress that because these processes are on different nodes, that often means that we're going to have communication of processes from different nodes. And that's why the networking is so important. So there's different patterns of communication that we define, and we're going to talk about two kind of families today. Those are point-to-point and collective calls. So point-to-point communication may be a send and receive, and this is exactly what it sounds like. You have one CPU that is sending a packet of data to another one. Hello, it's me. I've got a packet of data that you might want to receive. And then hopefully the other CPU is going to send a message back, or otherwise, the first CPU is going to be making music videos in black and white that are really sad, and you know how that goes. So the second pattern is called collective, and these are communications between collections or groups of processes. So here you see an example of MPI sum. This is a little like MapReduce, where you start with a bunch of numbers and then they're reduced down to one sum. Now, the most common collective call is called MPI all reduce. This is going to add something called MPI beatcast, which is going to broadcast that data out to more than one CPU. And we can actually look at these calls for collective and point-to-point across HPC applications. And as I mentioned, MPI all reduce is the most popular collective call, and then send and receive are the most popular point-to-point functions. So I must stress that because of these communication patterns, without a low latency network, the apps absolutely cannot be performant. So the OSU benchmarks are going to allow us to measure these through two things: OSU all reduce for collective, OSU latency for point-to-point. And we're going to be using the metrics operator. Here's what that looks like to create a metric set. And the goal of the metrics operator is just really make it stupid easy to run these HPC apps and applications powered by JobSet. Alrighty, so here we're looking at OSU latency. This is a point-to-point benchmark. On the cloud, we see latency in microseconds in log scale as a function of the packet size. And you're probably looking at this like, well, how do I know if this is any good? Well, we can compare it to HPC, which is orders of magnitude better, between 10 and 20 times, depending on where you are in this graph. And so I looked at this and my little abyss of expectations, and I was like, oh, it's the latency. I knew it. That's the culprit. But I also had another malformed expectation. Wink, wink. I thought that I knew that my application would run better on HPC. I assumed that it would run better, but I hadn't actually run it yet. Oops. And at this time, there was also sort of a blessing in disguise, which sucked at the time. But the blessing was that I did not have quota. So the instance type that I wanted to use, I didn't have quota for. So I had to fall back to a different instance type that I hadn't really tested as much. And I was shocked. So remember, we talked about strong scaling. The strong scaling looked beautiful. We saw that as we increased the MPI ranks, this time went down. And although this wasn't like the best that I'd ever seen, I was like in shock because this was the result that I had wanted to see way back in May, many months earlier. And so I'm sitting in my abyss of expectations with a nice stewing pot of confusion, like, what just happened? This didn't even work before. And of course, my confusion very quickly turned into delusion. I was like, it's okay. I'm still going to try an HPC and I'm sure it will be better. Again, shook. So what you're looking at here, we added in HPC, the cloud, it has the red boxes around it. And what we actually see is that the cloud times were faster for our MPI application, except for the largest size where one of our HPC clusters was slightly faster. And so what that suggests is there's still some issue with communication between nodes when we get to those larger sizes. What could be that cost? What's going on here? And we can actually then look at our all reduced benchmark, because that is a proxy for communication. So I know this looks like someone like sneezed on the slide, but let me try to explain what you're looking at here. You're still looking at average latency in microseconds in log scale as the function of the packet size. There's two groups here. The top group, this is cloud, and those little dots in between are actually an increase in cluster size. So the dot on the bottom is the smallest, the one on the top is the largest. And so what you see is that as you add more nodes that need to talk together, the time goes up a lot. Now, HPC is the second group, and it's much lower. Again, orders of magnitude, and this is a cluster that has InfiniBand fabric. And look at the difference in units. I just want to point out, these are sort of in the tens versus over 100. So there is a very large difference. So we do suspect that network is still becoming an issue at these larger sizes. So how could we further look at this? Well, we brought in our metrics operator again that also can run a tool called the HPC toolkit, because we wanted to verify that the time spent in all reduced was actually going up. And I was running out of cloud credit, so I only could run this on 3 sizes. But what we saw is that as the size increased, indeed, the time in all reduced, the time spent communicating between nodes was increasing. And this, in a way, did validate what we thought. Communication is definitely the bottleneck at larger sizes. So I can say this comically now, but I woke up the next morning after all of this, after these results, and being surprised, and I was overwhelmed. There were so many variables to think about. The story was not clear and logical, and there were still so many things I wanted to test, and it totally went against my expectation. This is why it's so dangerous to be in this abyss, and it felt really bad. But this is also why it's so important to have a supportive team, because my team came down and they were like, hey, V, it's a little dark down here. I know you're having some kind of party or something, but maybe it's time to come back up. And so we left the cave of debugging, and we had learned so much. And actually, the first point was almost joyful. We were like, wow, we were actually wrong about always having the need for the lowest of latency. The latency doesn't have to be super low. It just has to be good enough. And in fact, our application problem is CPU bound at lower ranks and network latency at higher ranks. And the reason it works so well on cloud is because the cloud has really awesome, shiny new CPU. So at this point, we could kind of return to the service. And this is where we are today. These are the things we still do not understand. We do not understand why this particular instance type did not work originally. We also need to better look at our expectations. What expectations or sort of lore do all of us carry that come from our community that might just be entirely wrong? And then application design. This is the coolest bit. How can we take our applications and kind of understand the patterns that they need to map them to the right environments? And so to kind of summarize the story, we started in this new space that we didn't understand. We found a design strategy to map between spaces. This was JobSet. And then we could figure out a means to easily measure and run things. This was the metrics operator that ran everything from proxy apps to benchmarks. And operators in Kubernetes are so cool. They are like developer Legos for building things. Highly recommend. In parallel, no pun intended, we also need to understand the application patterns and needs so that we can really best optimize the environment for them. And you know what? These are really complex, hard problems. This is not just the work that one team can do, not even one lab. We need to bring in collaborators from, not other labs, industry, academic, all over the place. And we have to work together on this to solve these hard problems. And, this is just the start. We are hoping to build a little bridge to get across HPC to cloud land. But really what we want to move toward is this future where we can have the best of both worlds, this converged computing. And you know what? There are a ton of adventures ahead, and we hope that you join us. I can't promise that I won't be out somewhere on an adventure, but you know what? You are invited to come to Kubecon. Back to you.